Let's get started. So, I guess he's not here today. He wasn't here earlier. Let me leave the door ajar. All right, let's get started. Today we're going to pick up from where we left off when we talked about breakpoint, and we're going to continue this discussion with the so-called VC dimension to kind of finish off this idea of a single number that you use to describe the complexity of a hypothesis set. And so, where we left off last time, we talked about, oops, there we go. We talked about an analytic solution, which is an upper bound for the number of dichotomies that a particular hypothesis set can produce given a data set of size n, a breakpoint of k. And we showed the recurrence relation, and we showed by induction that it holds true. And we looked at this upper bound, this approximation, and we proved that directly. And so given this upper bound, we also showed that it is polynomial in a polynomial um, uh, in the number of it's polynomial in this in the input size. I'm trying to remember. And so we showed all that, and we assumed true for the base case and showed for the inductive case. And so then we went back and we showed that from before, using those very simple hypotheses, the positive ray, the positive interval. We showed from before, we did the exhaustive counting to show the number of dichotomies that each one of these can generate. And we went back and we verified this with our upper bound, and it holds true. And then we left off last time, we showed what it would be for the 2D perceptron, but we didn't plug in all the numbers to compute. That's something you could certainly calculate pretty easily. So that's where we left off. Any questions about this? No? Okay. So let's take a look at the so-called VC bound. And so when we talked about this idea of Hoeffding's inequality, we were looking at the probability of a bad event happening. And this bad event was based on in sample error, diverging from out of sample error by more than some threshold epsilon. And uh, in this figure, we depict the space of data sets, and a single dot in this figure represents a single instantiation of a data set. So you can imagine when we talked about the probability in the anatomy of a learner, and that probability was responsible for giving us all the possible values. Essentially, that probability governs the data sets that we can arrive upon or that are given to us, all the possible data sets. And so with Hoeffding's inequality, we had some number of ways we can select that data set, but some choices of that data set will see in-sample error and out-of-sample error diverge from one another. But still, the difficulty was with this E out. Now, E in, certainly you have a set of samples, and with E out, you're talking about an expectation governed by probability, which is the probability overall of the data set instantiations that you can form. Now, given the space of data sets, there's some choices of data set for which these bad events will happen, i.e. out of sample error will diverge from in sample error. So essentially, if you identify or were to identify, and this is a theoretical argument, if you were to identify all these possible bad events, you would sort of scratch out or highlight a region in your space of possible data sets that might look like the following, right? So that's just a depiction, and we looked at Hoeffding's inequality as a way to think about the interactions as it pertains to the right context that assures that your in-sample error will track closely with your out-of-sample error. And so the Hoeffding's inequality worked with a single data set. And then we expanded this definition to work with the multiple hypothesis set because in the anatomy of a learner, we have multiple hypotheses that the learning algorithm searches through when it's trying to find the following best hypothesis. And so with Hoeffding's inequality, we made the worst case assumption to give ourselves a pretty conservative or loose bound, and we assume that all of these bad events are non-overlapping. And so from the Venn diagram standpoint, if you were to look at all of those instantiations of data sets for which out-of-sample error diverges from in-sample error by more than some error tolerance epsilon, if you assume that they're non-overlapping, essentially these clouds, if you will, corresponding to those data sets for which that's the case, where you get that bad event happening, this divergence, they're non-overlapping. And if they're non-overlapping and you have very many of them or some number of them, eventually you're going to fill up all this possible sets of data that you can compose, right? So that's pretty bad, and that just shows what one of the difficulties is with the union bound. Yes, it's a simplifying assumption, assuming that bad events do not overlap. But as we saw when we started talking about dichotomies, that a lot of these bad events do overlap because you can have hypotheses that are very similar to one another, and meaning that they generate the same labeling of +1, -1 associated with each of the in-sample points, but the value of the parameter vector corresponding to the hypothesis is different. And so we moved away from the union bound and we came up with this idea of a breakpoint and a dichotomy. And the VC bound also makes this assumption. It's related to the breakpoint and it's related to the number of dichotomies that we talked about when we talked about the growth function. And what the VC bound assumes is that there's a high degree of overlap between these bad events. And if you think about it, if you have a real valued hypothesis, a perceptron, where you have a weight vector governing that hypothesis, you can have two hypotheses associated with different weight vectors that produce exactly the same dichotomy. And so you can have a large count of these bad events that are overlapping with one another in this Venn diagram of possible data sets for which in-sample error diverges from out-of-sample error. And so with this VC bound, we talk about the hypothesis, its descriptiveness, in terms of dichotomies, but we make this assumption that these bad events can overlap to a large degree in many parts of our space of possible data sets. So in doing so, we make a much more conservative bound when it comes to the extension of Herfting's inequality, and that's in contrast to what happened when we had the union bound. And in doing so, you'll notice here that a smaller part of the space of possible data sets is covered by the union, if you will, of these bad events. And so that means that a relatively smaller probability you'll have associated with the likelihood that E in and E out are going to diverge from one another by more than your epsilon. And so what this depiction says is that this idea of working with dichotomies is a nice collapsing argument, right? Unlike the union bound, we assumed that the bad event was non-overlapping, but in truth, we see that if you have one particular dichotomy, you can have very many hypotheses that can generate that particular dichotomy, essentially collapsing this probability of bad events so that they're non-overlapping, and the end result is that E in and E out diverging from one another would be much more conservative, i.e. a smaller probability. Does that make sense? Okay, so let's go on. But there's another problem with this. Now the problem has to do with E out. Now out of sample error, yes, it does exist, and we talked about the probability associated with these out of sample points, and that probability, we argued, is responsible for giving you the data points or the data set values, the feature values associated with all of the observations you could have out of sample. Now, if you could eliminate out of sample error, right, do away with this probability associated with out of sample data, it'd be a lot easier to do these analysis to start to reason about the size of this area carved out by the so-called bad events that can occur, right? Because that drives what your generalization performance is going to be like. So one of the things you can do, and here we have the balls and bins example again, and we were talking about Herfting's inequality. We had our in-sample points and we had our out-of-sample points. And we draw some sample and we're measuring the proportion of red marbles relative to all the marbles you took in your in-sample points, E in, versus out-of-sample. Now, if you can draw a single hypothesis, to talk about learning being feasible, certainly you can make two different draws from your set of your marbles in your bin. And so if you do that with the same governing distribution, you may very well get a different set of marbles in your set of in-sample points. So let's do that, and we draw n many data points, and we associate that error, in-sample error, we call that En, for a specific hypothesis. And then we're going to make another draw of n many points, so we have a total of 2n data points that we draw in sample. And that second set of n data points, we're going to call that En prime of H. So now, if we draw 2n samples, the first set of n and the second set of n, we can keep drawing those samples enough times. Essentially, En of H is going to be very different from En prime of H, right? If you do it enough times, you might draw it once, look at it, oh, they're close. Do it again, oh, they're close. Do it again, oh, they're close. But if you draw 2n samples, a first round of n for En of H, a second round of n, many samples in sample points, En prime of H. If you do this enough times, you're going to get some draw of 2n points such that En of H is going to be different from En prime of H, right? Because you just might hit that one pathological example where the luck of the draw favors En of prime of H being very, very different. You might have a lot of mostly red marbles for En prime of H and mostly green marbles for En of H. And it's very possible to do that. In fact, you could try that experiment yourself. So nonetheless, if you have these two samples, you can essentially get them to be different from one another. Well, we know, given Hoeffding's inequality, that in-sample error tracks with out-of-sample error. So that means out-of-sample error is going to be close to in-sample error. And likewise for the second draw, out-of-sample error is going to be close or track closely. If you choose the conditions well, it's going to track closely with En prime. So that means now, if you compare the performance of En of H with En prime of H, and you look at them relative to one another, if En and En prime of H diverge from one another, that says something about the relationship between E out and En. Because if you can make two successive draws and get the in-sample error, which you have control over, you can get them to diverge greatly. Maybe you can use the relationship between these ENs, En of H and En prime of H, as a substitute for comparing out-of-sample error with in-sample error, right? Because they both track with out-of-sample error, so you're using the relationship between En and En prime of H to talk about whether or not learning is feasible. Does that make sense? And so there's a whole proof about this, and it's in the Appendix A in the book, and it talks about what's called the VC bound. Okay, and so this is what it looks like. And we talked about the original learning scenario where we took our growth function and we replaced as the complexity of our hypothesis at big M, we replaced that with M sub h of n. And n sub h of n was a so-called growth function, and that growth function returned back the number of dichotomies that hypothesis h can generate. And so with this comparison of En of H and En prime of H, we get an equivalent expression that looks at the relationship between in-sample error and out-of-sample error by comparing the performance of the first draw for the hypothesis set against the second draw. Now, it's in Appendix A, and maybe as time permits, we might take an opportunity to look at the original paper that talks about the VC bound. It's a really, really important aspect of machine learning because it governs or defines the right conditions that you can set and the trade-off between those various controlling factors that makes learning feasible. Does something generalize well out of sample? Okay. And so the expression we get, we have the probabilistic bound, that bad event, that in-sample error for a final best hypothesis diverges from E out of your best hypothesis by greater than some epsilon is at most 4 M sub H of 2n because you have twice as many samples from the first draw and the second draw. And in the original proof, you get a term that's epsilon over 4. If you square that, that's epsilon over 16, and that's where you get that minus 1/8. So I won't go over the details, but this is the actual result from the VC bound from the literature, and we'll take the time at some point, if time permits, to actually go through the published version of that proof, but it is in Appendix A of the book. Okay? All right. Any questions about this? And so what Vapnik and Chern, I keep mispronouncing the last name, Cernavenkis, something like that, what VC Vapnik and Cernavenkis did was they made an insightful uh, observation that if you take true draws, because out of sample error tracks with in sample error, if you take two draws, you can get the same effect by comparing the first draw against the second draw in sample. And so you get around this idea of managing this out of sample error that you don't have control over. And then you take those two expressions and combine them, and you get the expression down below. Okay? All right, so we'll certainly try to take time in the schedule to go through the original paper that actually does the proof or develops this theory. Okay? All right. So let's take a look at what the definition of the VC dimension is. So the VC dimension, it's pretty simple. The VC dimension is associated with the hypothesis set. So when you talk about hypothesis set, certainly you talk about its complexity. A hypothesis set has a VC dimension, and it's a measurement or description of the descriptive power, if you will, of a hypothesis set. So you can now compare the complexity or the descriptiveness of a hypothesis set on equal footing. Okay, so the VC dimension of a hypothesis set H, or DVC of H, is the largest n, data set size, number of in-sample points, for which the growth function can generate 2 to the n total dichotomies. Now, this looks a lot like the growth function. Yes, when we talked about breakpoint, we talked about that data set size where it can no longer produce all 2 to the n dichotomies. With the VC dimension, it's related to breakpoint. It's the largest data set size for which that hypothesis set can shatter the data set, can produce all 2 to the n dichotomies. Okay. Any questions about this? So what does this mean? It means that if you have a data set of size n, if n is at most the VC dimension of that hypothesis set, that means H, the hypothesis set, can shatter n many points. So if it can shatter n many points, it can certainly shatter n minus 1 points. It can certainly shatter n minus 2. And so we use less than equal to when we describe the relationship between the VC dimension and the size of the data set. The breakpoint is related to the VC dimension. The breakpoint from before is that data set size K for which the hypothesis set H can no longer generate all 2 to the H, 2 to the n many dichotomies. And so K, our breakpoint, is greater than the VC dimension of the hypothesis set H. And that's what it means to be a breakpoint. It means you can no longer keep up with the number of dichotomies possible 2 to the n. And so the breakpoint is usually one more than the VC dimension. Does that make sense? All right. Any questions about this? All right. So relative to the breakpoint, when we made that approximation, that polynomial approximation that bounds from above the growth function, we had the following expression. We said the growth function, m of h, for a data set of size n, is at most the sum for I goes from 0 to k minus 1 of n choose I. Now, relative to VC dimension, we said the VC dimension is 1 less than the breakpoint. And you'll notice here in our expression relative to the breakpoint, we said the growth function is at most 1 less than the breakpoint in this summation. If you look at the index upper bound on that summation. So relative to the VC dimension, if we are looking at the growth function, we say the growth function is at most the sum for I goes from 0 to the VC dimension of n choose I. And as such, if we look at what the definition is for n choose I, the largest term in this expression, in this summation, is where we have n choose DVC, right? And if we look at that and expand out what combination means, we get a polynomial where that polynomial has degree of DVC, which is the VC dimension. Does that make sense? So from before, if you expand it out, what n choose I is, and you look at the upper bound of this summation, it will be n choose DVC, and that is certainly an expression that's polynomial where the degree is DVC. Polynomial in the size of the data set, the number of in-sample points. Okay, any questions about this? All right, does that make sense? Okay, so that's our growth function as it relates to DVC, our VC dimension. And going back to the three examples we gave, we have the positive rays. And so the positive rays, the largest data set for which the positive ray hypothesis set could generate all dichotomies, was a data set of size 1. Once we went to a data set of size 2, it can no longer generate all 2 to the n dichotomies, and therefore the VC dimension, DVC, of the positive rays is 1. When we look at the 2D perceptron, we went on the plane, the 2D perceptron on the plane. We went from a data set of size 3, and when we went to a data set of size 4, we could no longer generate all 2 to the n many dichotomies. And so we would write the VC dimension for the 2D perceptron is going to be 3. So DVC is equal to 3. And then we saw the set of convex sets. We said for any data set of size n, as n goes from 1 to infinity, well, the hypothesis set consisting of the convex sets can generate all possible 2 to the n dichotomies regardless of the data set size n. And so there we'd say the VC dimension is infinite, right? Because we can keep going up and up and up and up in the limit as the data set size approaches infinity, and you're just going to have an infinite number or a large number of data points around the circle. You just assign any +1, -1 labeling, you connect the positive points, and then everything in that region, that polytope formed by the convex set, formed by connecting the positive points, those are positive, and everything outside is classified as negative, right? The VC dimension for the convex sets is infinite. So if you look at it, well, we see that the convex sets are more descriptive than the 2D perceptron, line in the plane, and the line in the plane is more descriptive than the positive rays. Okay. Any questions about this? Does it make sense? Yeah. All right. So um, let's take a look at the implication in our anatomy of the learner, the implication of VC dimension on learning. And so we said that if the growth function is polynomial, it means that learning is feasible, meaning that we can generalize well out of sample, meaning that in-sample error tracks well or isn't too far away from out-of-sample error. And so what this polynomial corresponds to is the VC dimension being finite, right? Because if it's finite, we know that that decaying exponential and Herftings inequality can certainly make that right-hand side of the inequality small enough corresponding to a very rare occurrence that that bad event is going to occur, because that's what you want for learning to be feasible. And so this VC dimension, DVC, of your hypothesis set being finite means that your final best hypothesis is going to generalize well, because it also means that your growth function, our measure of hypothesis set complexity, will be polynomial. And so when we express this idea of VC dimension, you notice we don't make any distinction about the learning algorithm employed. How do you select this final best hypothesis? And that's on purpose. It's divorced from the method, and it talks about the descriptive power of the class of functions you're considering in your learning model. It also doesn't depend on the input distribution. It's a combinatorial argument, or it derives from a combinatorial argument based on the labeling of +1, -1 that you can assign to your in-sample points. And because it doesn't depend on the input distribution, you don't have to worry about this idea of expectations using this probability distribution that was responsible for giving you your data vector values. It also doesn't depend on the target function, right? It only depends on in-sample error, things that you have control over, namely looking at the labeling this combinatorial argument, the labeling of dichotomies or +1, -1 labelings associated with the in-sample points. But it does depend on H, your hypothesis set. It depends on your training examples, and it certainly depends on your final best hypothesis. So it's a nice kind of very flexible single number, this VC dimension, that you can use to compare descriptive power, but it frees you from worrying about things you don't have very much control over. Okay? All right. So let's take a look at the VC dimension of the perceptron. And so we're going to make some argumentative proofs here, and we'll come upon a solution for two different cases. And so for the 2D perceptron, we saw that for a two-dimensional perceptron, that's two weight vectors, W1, W2, and that was a line in the plane, we saw that the VC dimension was 3. When we went from 3 data points to 4 data points, we no longer could produce all 2 to the n dichotomies. But generally, for the perceptron, the VC dimension, dVC, is going to be d plus 1, where d is the dimensionality of the input representation. So for the 2D perceptron, well, the dimensionality was 2, and that was the dimensionality before we augment that matrix. We augment our x vectors with an x naught, and then we augment our weight vector with a w naught. So when I say the dimensionality, I mean the original input dimensionality, right? So when we talked about the 2D perceptron, we talked about a line in the plane, and the VC dimension was 3. When we got to 3 data points, yes, we could generate all 8 dichotomies, but when we went to 4, we could no longer generate all 16 dichotomies. Okay, but let's prove the general form of the perceptron. If we went to more than 2 dimensions, the general scheme or the general complexity for the perceptron in d plus in d dimensions, the VC dimension is 1 more than the number of dimensions in the original input representation. So if we had a 4-dimensional perceptron, the VC dimension would be 5. Here we have a 2-dimensional perceptron. The VC dimension is 2 plus 1, which is 3, right? So what we're going to do, we're going to prove this by solving two things, by showing two things. One, that the VC dimension is at most d plus 1, right? And also we're going to show the VC dimension at the same time is at least d plus 1. Now, of course, if you can show at most and at least, what remains is equality. And that's one way you can prove equality. Does that make sense? Okay. So let's do that. And what we're going to do is we're going to focus first on the first case. The VC dimension is at least d plus 1, right? And so how we're going to do that is we're going to define a representation, and we're going to choose some data points. Now remember, when we talk about VC dimension, we're talking about dichotomies. And when we talk about dichotomies, we can set or make any choice that we want for the individual feature values associated with each one of our data points. Now, before we had a line in the plane, that was 2 dimensions. Here, we have 3-dimensional representation. So we have 3 features: the first feature, the second feature, and the third feature, right? And so one of the arrangements we're going to choose is we're going to have a point that is a data set that has 1 more data point than you have dimensions. Here we have 3 dimensions, and so we're going to construct a data set consisting of 4 data points. Now, of course, in this regard here, you'll notice that if you select it this way, well, you can always find a hyperplane, a sheet that will separate all these data points and generate all possible dichotomies. Because the problem we had on the plane was we couldn't split the 2 points in the middle from the 2 points on the sides, right? We couldn't assign one of them as positive and the other as negative because the line wouldn't allow us to do that. But if we choose our feature values appropriately in 4 dimensions, we can absolutely produce all possible labelings, and I'll show you mathematically how that's possible. So if you have one point if you have enough data points, we have the count of points n, the size of your data set, n is one more than the number of dimensions. In this case, we have 3 dimensions, but we have 4 data points. So what is a fact about this? Now, regardless of the value that we choose, we can always take that d plus 1th point, so we have 3 dimensions, d plus 1 is 4. We can always take that 4th point, and we can always express that as a linear combination of the other points. If you don't believe it, well, what's one arrangement you can have? You can have one point that is 0, 0 on all the axes along the first axis, 0, 0 for the other two, and only non-zero along the third, and non-zero only along the other axis. And then any point you can form as a fourth point is literally a linear combination, right? So we can absolutely do that. And that is without loss of generality, regardless of the number of dimensions. So if you have one more point than you have dimensions, you can find an arrangement. Now remember, when we talked about dichotomies, it didn't matter what the feature values are, right? And so I'm going to choose feature values so that each of the data points are aligned with the axes, right? So that's 3 axes, 3 data points. And any fourth data point, it doesn't matter where it is, you can always express it as a linear combination of the axis aligned data points. Does that make sense? And I can absolutely do that because when I'm talking about counting dichotomies, it doesn't matter what the feature values are. So I can set whatever values are for those points in 3 dimensions. Okay? All right. So if I have one more data point than dimensions, that d plus 1th point can always be computed by a linear combination of those other points, those d many points. And I can always choose an arrangement where that's true, regardless of the dimensionality. But I'm only showing it for 3 dimensions here and 4 points because I can only do that with 3 dimensions on the board. Okay? All right, does that make sense? All right, so let's take a look at what these will look like. So here I have my vectors, and it doesn't matter how many dimensions I have. In the example in the previous slide, I had 3 dimensions, so I have 4 data points. But for an arbitrary d dimensions, I have d plus 1 data points, and I'm going to arrange these in a design matrix. So here you'll see I have d plus 1 rows, where in each row is a single data point. Does that make sense? All right. So if I look at the columns of a particular vector, remember when we have a vector in d dimensions, we have d plus 1 data points in d dimensions. So if a vector is in d dimensions, remember I augment each of my vectors. So I have d positions in each vector, and I augment each vector with an x naught, and that x naught is a fixed value of 1. So if I look at, say, the first vector, x1 transpose, the first row of my design matrix, well, if I look at the first column here, that's for x naught. The next column is for x1, next column is for x2, x3, x4, and so forth. And so you notice here the first column is all ones because my x naught is always all ones. So I have x1 to xd, right? Second column through the d plus 1th column. But my first column there, the x naught column, it's all ones. So that gives me a rank of d plus 1 for each of these input vectors. I have d dimensions here, x1 through xd, and I have x naught, it adds 1 more, so I have a total rank of d plus 1 for each of my vectors. Does that make sense? So I have a d-dimensional vector, I augment each one with x naught to make it a d plus 1 dimensional vector. Okay? All right. So what this gives me is a square design matrix. It's square because each column, I have d plus 1 columns, and I have d plus 1 rows, because when I constructed or defined this data set, I said, give me one more data points than I have dimensions. And then each one in d dimensions, I augment with my x naught. So therefore, this design matrix is square. And because it's square, it's also invertible, right? That's a really important concept in the proof. Does that make sense? All right. So I have this square design matrix, and because it's square, it's invertible. I have augmented my data points with an x naught, and the data set was originally d dimensions. Now it's d plus 1. All right, and I have d plus 1 more vector than I do have dimensions. All right. So now what I'm going to do is I'm going to define a vector of my y values, my labels. Now these labels, I have d plus 1 labels. Why do I have d plus 1 labels? Because I said, give me one more feature, one more input data point vector, one more than I have dimensions. So if I have d plus 1 rows representing d plus 1 data points, I'm going to have a label y for each one of those d plus 1 vectors. So I have y1, y2, y3, etc., up to and including y sub d plus 1. So I collect them all together as a column vector of labels, and I call that my vector y, right? And so y, I can assign any possible labeling, +1 or -1, in each of the d plus 1 positions of my column vector y. Does that make sense? Yes. Ah, because y is the label for each one of these d plus 1 vectors, right? So each vector, I'm defining a data set, and I want to show that you can that the number of dichotomies is at least d plus 1, right? Associated with the data set size of d plus 1. So I take an input representation and I say, how many dimensions do I have? If I have d dimensions, I want d plus 1 data points. So here are my d plus 1 data points, and each one is a vector in d dimensions. I augment it with x naught. Now I need the label associated with x1, the label plus or minus +1 or -1 associated with x2, x3, and up to and including xd plus 1. And so this y vector, it's the set of labels associated with each one of those vectors. Does that make sense? Okay. Any other questions? No? All right. So I have my label matrix, and this label matrix, it doesn't matter what my assignment of +1 and -1 is. Given any assignment of +1, -1, i.e. any dichotomy, I can find the W vector that gives me this labeling, right? So what does that mean? It means I can actually, in closed form, calculate what the hypothesis is that shatters the data set. I can produce all possible dichotomies. So let's find that W. So what do I do to classify? Well, if I have a classifier whose weight vector is W, I compute sine XW. So that's just multiplying my design matrix times a weight matrix. And I set that equal to Y. So if X sine of XW equals Y, that means the output of my classifier, right? W transpose for X1, W transpose X2, W transpose X3, and so forth, that's equal to that +1 or that -1 label when I take the sign of that. And so that being the case, if I set xw equal to y, right? Now, certainly if xw, if each position of xw is positive, and it exactly matches y, then the sign of it will also match the label of y, right? So then, because x is invertible, I left multiply both sides of equality by x inverse. And so the x design matrix goes to identity. I'm left with w is equal to x inverse times y. Okay? All right. Any questions about this? And that's certainly something you can do in like 3 or 4 lines of MATLAB. Okay, so this means, yes, absolutely, I can shatter this data set. I can produce any possible labeling of +1, -1 to these associated with these dichotomies, possible dichotomies that I can form. Okay, so this demonstrates the first case that I can, if the VC dimension, DVC, is at least D plus 1, where D is the dimensionality of the original input representation plus 1, right? So I've demonstrated that. I've demonstrated that with this construction, I can produce all possible dichotomies 2 to the n, or rather more correctly, the VC dimension is at least the dimensionality of the data set plus 1. And I've actually demonstrated that here with this construction. Does that make sense? So I didn't set any restriction on the feature values. I took an example where the number of data points is one more than the dimensionality. I showed you this construction and actually showed you that I can find a W that generates any +1, -1 labeling. Okay, so it's at least D plus 1, where D is the dimensionality. my VC dimension. And remember, VC dimension is the number of dichotomies, the size of the data set for which you can produce all 2 to the n dichotomies. Does that make sense? All right. Any questions about this? Yes. Mm-hmm. Is DVC is one less than the breakpoint. Breakpoint is that data set size where the hypothesis set can no longer produce all 2 to the n dichotomies. But the VC dimension is related directly to the growth function. VC dimension is the data set size where you can produce all 2 to the n dichotomies, where the growth function is how you measure the dichotomies. The VC dimension is that point where it can continue to generate all possible dichotomies. Now, of course, here, this relationship talks about the relationship between the VC dimension and the dimensionality of the input representation. That's a different statement from talking about the growth function, the number of dichotomies. Does that make sense? Okay. Yes. Yes. Um, it's always what? Yes, it's always one more than the VC dimension because it breaks, but it isn't necessarily 2 times, right? Because what the breakpoint says that when I go from when I have a data set of size n, right? Um, if that's my VC dimension at size n, I can generate 2 to the n, right? Dichotomies. But once I go to bigger than n, I can no longer generate 2 to the n. So it could be, let's say for the perceptron, we saw that when we go from 3 to 4, we can no longer generate 2 to the n. So we couldn't generate 16, we could generate 14, right? But it could have been for some other hypothesis when you go from 3 to 4, instead of generating 14, it could be that you can only generate 10 out of the 16, or you can only generate 9 out of the 16. And so that's why I make draw a distinction, because it's not necessarily a doubling, right? It's just that point where you increase the data set, the hypothesis set can no longer keep up with the 2 to the n. So you could be really close to 2 to the n, right? N goes from 3 to 4. Maybe you can compute or generate 15 dichotomies, right? Or maybe you can only generate 9 dichotomies when you go from 3 data points to 4. So it's not necessarily twice. It's you can no longer keep up. And I make that kind of really picky distinction because we don't know how close it gets to the 2 to the n. We just know it can no longer generate 2 to the n. Does that make sense? Okay. All right. Any other questions? No? All right. Let me check the time. 5:14. All right. So let's now let's now demonstrate or prove the other point that the VC dimension at the same time is at most d plus 1, right? Because we need that condition that less than equal to, that inequality, to show that the VC dimension is exactly d plus 1. So we just got done showing the VC dimension is at least d plus 1, where d is the dimensionality of the original input representation. And now we're going to show that other case less than equal to. And so how we're going to do this is we're going to show that we cannot shatter at most d plus 2 points. Because if we show that we cannot shatter any d plus 2 points, it means that we're going to be at most d plus 1. Okay? All right. So let's do that. So we're going to assume a data set, and these are vector valued, x1, x2, x3, x4, and so forth. And in this case, each one of these input vectors x has d dimensions, right? D could be 2, d could be 3. It doesn't matter how many dimensions it is. But the number of data points we have in d dimensions, the number of data points we have are in sample, our n, the size of the set of in-sample points is going to be d plus 2. So for example, if we had 3 dimensions, that means we're going to have 3 plus 2 data points, which is 5 data points. Okay? All right. So we have a data set size where the size of the data set is 2 more than the input dimensionality representation. And so you have more data points than dimensions. And if you have more data points than dimensions, as we said before, that there are some data points, let's call them of the form xj, that are linear combinations of the other data points. And we saw in the first proof that we just got done doing, that you can absolutely construct a data set like that, right? Okay, so we have xj, that's our synthesized point, I'll call it that, just to give it a name, and xj is one of these d plus 2 data points, and that because we have more data points than dimensions, we can construct xj by some linear combination, a set of weights, ai, times all the other data points, xi. So when you make these linear combinations, if you construct xj, xj doesn't have to be a linear combination of all of the other data points, right? Some of those data points will contribute nothing, right? Some of them will contribute positively, some of them will contribute negatively to the eventual sum, which leads to your xj. So some of these coefficients ai that lead to the linear combination that synthesizes our xj data points, right? Some of these will be zeros, right? It doesn't have to be all the data points that contribute to the value of the synthesized data point. But if some are zeros, some are non-zeros. Those are the ones that contribute, right? And so some of these AI coefficients that you use to synthesize this xj data points, some of them are going to be non-zero, some are going to be zero. Now for the non-zero ones, some of these coefficients are going to be positive, and some of these coefficients are going to be negative, okay? So let's construct a data set, and we're also going to come up with a scheme for constructing a dichotomy that we're going to use to prove that you cannot shatter any d plus 2 data points, right? Okay. So let's choose a dichotomy where, again, a dichotomy is an assignment of +1, -1 labels. And so we're going to do it in the following scheme. So let's take all of the xi's that contribute to the linear sum for the synthesized data points, and all of those with a non-zero coefficient ai are going to get a label that is +1 if ai is positive and -1 if ai is negative. Said differently, that means the label associated with each xi that contributes to the synthesized point, the coefficient ai is going to be the same as the label associated with xi. Does that make sense? So ai is going to be positive if yi is positive. ai is going to be negative if yi is negative, right? Okay. So then, in addition, that corresponds to, or that gives us a +1, -1 labeling for each one of these xi's that contribute to a synthesized xj. Now for the xj, we're just going to fix its label to be -1, okay, in this scheme. So we've come up with a dichotomy, a way of assigning +1 and -1 labels to all of the data points. And these data points, there are d plus 2 of them in d dimensions. Some of them are synthesized, and some of them are not synthesized. And we have a labeling for each one, okay? Any questions about this? All right, so no perceptron is able to shatter this dichotomy. Now, of course, to shatter a data set, what does shatter mean? It means that you can produce all possible 2 to the n dichotomies. Now, this is a dichotomy. Yes, it's a strange dichotomy, a strange way of assigning a dichotomy, but this is one of the 2 to the n many dichotomies that you can associate with a data set of size d plus 2. Now, it doesn't matter how you construct the dichotomy, we have one of the 2 to the n. And we're going to show that no perceptron is able to shatter this particular dichotomy. Now, if it can't shatter this particular dichotomy, at least for this dichotomy, it's going to fall short of that 2 to the n by this, and therefore can't shatter the data set. Does that make sense? Okay, so let's take this definition and carry it forward and show you that we can't possibly shatter this particular dichotomy, thus falling short of this 2 to the n. All right, so let's take a look at this. So we said the synthesized data point xj is a weighted sum of all the xi's that are non-synthesized. Now, of course, if we want to compute the classification given a hypothesis and we don't make any restriction on what the weight vector w is, well, how do you do this? You say w transpose xj, right? Because that should output the label associated with xj. If it's positive, it'll output it be positive. If it's negative, W transpose xj, it should produce a negative value, and that will correspond to the label of xj if it's a -1, right? We just got done saying that xj's label for this dichotomy, we're going to fix it to -1, right? And so we should be able to find a hypothesis if it can shatter that data set with d plus 2 data points. We should be able to find a hypothesis such that W transpose xj is a negative quantity, okay? So let's do this. So if we compute W transpose xj, well, what is xj? Xj is just this linear combination. W transpose, well, that's a vector of scalars, right? A vector of numbers. And so we can substitute for this xj, we can substitute this weighted sum. And what does that give us? Well, if we multiply a scalar times two variables, it doesn't matter if the scalar is outside of the sum or inside of the sum, right? This distributive property. We can perform the sum first, or we can distribute that multiplication over the summation. So if we distribute that multiplication by W transpose into that summation, which is our linear combination defining our xj, what we get is the sum for all I not equal to j of ai, the coefficient, times xi, but we're also multiplying by that W transpose. Does that make sense? Okay. So if we do that, well, let's make an observation. So we have ai, we have W transpose, and we have xi. Now, if the class label of xi is positive, we said that ai is also positive. So what does that mean? Well, if the class label associated with xi, the yi, is positive, that means by definition, W transpose xi is going to be positive, right? Because sign of W transpose x is going to be the class label. And if that class label is positive, then that W transpose x has to be positive, okay? Now, if we take a positive product, a positive quantity, W transpose x, we multiply by ai, which is also positive, that means this whole expression, that term in the sum, ai W transpose xi, that's going to be positive, right? Okay, so let's take into consideration those terms for which ai is negative. Now, we said ai is negative. That corresponds to an input vector xi whose class label is -1. So if the class label is -1, that means W transpose xi is going to be a negative quantity, because it'd be a negative quantity because we're going to do sine W transpose x, and that's its class label. So if this quantity W transpose x is negative, ai is also negative because it means the class label for xi is negative. So we have a negative quantity W transpose xi, and we have a negative quantity ai. Negative times negative is, again, positive. So what does that mean? It means this term underneath the summation, ai W transpose xi, it's always greater than 0, regardless of whether ai is positive or ai is negative. Because of that W transpose x, it's going to be the same sign as the sign on that ai. Does that make sense? So, yes. Why is the class label? It's always +1 or -1. If ai is 0, this does not contribute to the sum, which results in xj. And so ai can absolutely be 0. If it's 0, it doesn't contribute. If it's non-zero, it can either be positive or negative contribution to the sum. Okay? All right. Any other questions? All right. So now what does that mean? It means every term that I sum is going to be positive, right? And if every term that I sum is positive, what that means is this W transpose xj must also be positive. If this W transpose xj is also positive, if it must be positive, sign of W transpose xj must also be positive. Do you agree? Any questions? That makes sense? So if all the terms in the sum are positive, that means W transpose xj, which was synthesized, is also positive. Now, if it's also positive, its class label should be positive. But guess what? Based on the original construction, we said xj, the synthesized point, gets a label of -1. So we have a mismatch, and we can't possibly generate a W that matches the class labeling based on this particular definition of a dichotomy. Now, this is one type of dichotomy that we've constructed, but this is just one of the 2 to the n many dichotomies for that data set of size d plus 2. Now, in order to shatter a data set, you have to be able to generate all possible 2 to the n, but we're doing that, we're disproving that by showing you here's a single dichotomy that it can't produce by definition. Does that make sense? Okay, so what does that mean? It contradicts the original sign associated with the synthesized data point xj. So that means we know for a fact it's at least one dichotomy shy of 2 to the n dichotomies for this d plus 2 size data set. If you're one dichotomy shy, that means you can't shatter a data set of size d plus 2 because you can't produce all 2 to the d plus 2 possible dichotomies. Does that make sense? And so that kind of goes back to the question that you had asked, Philip, that when you talk about breakpoint, is it doubling? Now, when you go from a data set for the 2D perceptron, when you go from a data set of size 2 to size 3 to size 4, we know that it can generate all 2 to the 3 or 8 dichotomies. We know that it can't generate all 2 to the 4. But when it can't generate all 2 to the 4 or 16 of them, it could be that it's generating 15 of them. It's one shy, like this case, or it could be it's generating just one more than 2 to the 3. It's just generating 9. And it doesn't matter when we talk about breakpoint, it doesn't matter where it lies. All that matters is that it can no longer keep up with the 2 to the n. That make sense? Okay, great. So we've just shown that here is a single dichotomy, and we haven't set any restrictions on the W. Here's a single dichotomy associated with a data set of size d to the n, and we've identified one of those 2 to the d to the d plus 2 power many dichotomies. Let me say that again. For a data set of size d to the d of size d plus 2, not d to the 2. For a data set of size d plus 2, we've shown that here is a single dichotomy out of that 2 to the d plus 2 power that it cannot generate. Okay? And you only need to show one to say it can't shatter, because to shatter, you have to generate all possible 2 to the n dichotomies. Okay? All right. Any questions about this? And so by contradiction, the sign of that synthesized data point xj, it should be -1, but we showed that it's +1, and it doesn't matter what the value of w is. This hypothesis w, weight vector, can't possibly produce this one type of dichotomy. Okay? All right. Any questions? Does that make sense? Okay. 529. All right. So we've just now demonstrated by identifying one dichotomy out of 2 to the n, and we've shown that if the VC dimension is dVC, it's at most d plus 1, and we showed that by demonstrating that it can't generate all 2 to the n for a data set of size d plus 2. Okay? All right. So what does that mean? We've shown that the VC dimension is at least d plus 1, where d is the dimensionality of the original input representation. We've shown that the VC dimension is at most d plus 1, and therefore equality holds since these two are satisfied. So we get the VC dimension is exactly d plus 1, where d is the dimensionality of the original input representation. Does that make sense? Okay, any questions about this? Okay. So there's our result for the 2D perceptron. And d plus 1 in the perceptron is also the number of parameters, if you look at it. So when we talked about the 2D perceptron, we started out with d dimensions, and we had weight vector w1, w2, w3 in our weight vector, and we had one position in our perceptron weight vector associated with each of the dimensions. So then we augmented with w naught, and w naught was originally intended to represent this threshold minus t from way, way back when we talked about PLA. So if you think about it, the number of parameters in the perceptron is d plus 1, which is exactly the descriptive power of this perceptron, right? And so that fits directly with the theory. So we have the original weights plus the threshold that we needed for the perceptron when we talked about the credit example. We said, is the weighted sum greater than the threshold, right? And so here we see that the perceptron, its VC dimension, is exactly the number of parameters associated with this learning model. Now, I say model differently from input representation. The model is the thing you use to learn with, and that's the augmented version of the weight vector, along with the augmented version of the original input feature vectors, your in-sample points. Does that make sense? All right, any questions about this? Yeah? All right, so let me pause. Okay, so let's kind of interpret, and we'll probably end with this part, 531. Let's interpret what VC dimension means. So we talked a little bit about the proof. We talked about dichotomies, but it's nice to have more of an intuition behind this idea of descriptive power as expressed by VC dimension. So if you ever go into a music studio, maybe you have, maybe you haven't, this is a soundboard from a music studio. And each one of these knobs, well, not each one, many of them, they represent ranges of frequencies for sound. And it's kind of scary, actually. They can isolate voices, certain types of voices. They can isolate very deep sounds, middle sounds, all sorts of things. And literally, they can take multiple sources and they could trim out everyone who has a deep voice out of a song and everyone who doesn't have a deep voice is left, and then insert a new deep voice to sing along. It's really crazy what they do. But nonetheless, we have these frequency knobs, and these knobs on the control board in a music studio represent some parameter that you can control. It could be the frequency. It could be the amount of energy in that audio signal at a certain frequency. It could be the amount of echo or background noise, all sorts of stuff. And so a parameter is a so-called degree of freedom. It's a way of controlling, similar to the soundboard, of controlling one aspect of your hypothesis. And so if you think about the equation for a line, y equals mx plus b, you have two parameters. You have the slope, m, and the y-intercept b. If you change b, what happens to that line? It moves up, it moves down, it moves up, it moves down. If you change m, the slope, what happens to that line? It tilts one way or tilts another way, clockwise or anti-clockwise, relative to the origin, right? And so each one of these so-called degrees of freedom gets your hypothesis to, or causes your hypothesis to move in some number of way. So if you combine those two degrees of freedom, you can get your line, if you will, to do this, as well as move up or down, to slant or move up or down. And any combination is a certain type of movement that you can get your hypothesis to make as you're searching through a set of hypotheses. Now, if you have more control knobs, what that gives you is a larger set of ways in which you can get your hypothesis to move, right? So a line can only move in two ways, or as controlled by two input factors. And these two input factors, each one is called a degree of freedom, right? So when you have an audio board, these are so-called analog degrees of freedom. But if you look at what VC dimension is doing, when you talk about the ability to generate dichotomies, that's kind of like an on-off. It's a binary set of degrees of freedom. And it describes the ways in which you can set these +1, -1 labels, your descriptiveness in terms of +1, -1 label assignments to these n many data points in your in-sample points, among your in-sample points. Does that make sense? And so a degree of freedom is a way of talking about how you can change the hypothesis. And so the larger your VC dimension, you can change these binary hypotheses, these different ways of assigning +1 and -1 in a more sophisticated way. Okay, so if we looked at the positive rays, we had this one parameter, the anchor point. And this anchor point, if you set it to be a large value or small value, you can get this hypothesis to change the dichotomy in one particular way, right? By moving the anchor point. Here for the positive intervals, the VC dimension is 2. And if you think about it, the parameters here, we have the left anchor point and the right anchor point. We have two different ways we can get this hypothesis to change the assignment of +1 and -1. And so you can think of degrees of freedom as the parameter of a hypothesis set, because the more parameters you can have, the more sophisticated ways you can get it to move these +1 and -1 labels around on the data set. Does that make sense? Okay, so here we have a set of perceptrons. And when you look at a model and you want to count or measure the complexity, you really need to take account for what are called the effective degrees of freedom. And I'll explain what I mean by that in this figure. And so each one of these perceptrons is in one dimension, and each perceptron, it has a weight vector in one dimension, and it has a threshold, also sometimes called a bias term. And so each one of these circles, the perceptron, is associated with a W and a W naught, a W1 and a W naught. They're one dimensional. Okay. So if you count the number of parameters for this entire cascade of one-dimensional perceptrons, you have 2 parameters for the first stage, 2 parameters for the second stage, 2 for the third stage, and 2 for the fourth stage. So naively, if you take this learning model, you say, aha, I have a perceptron, and the number of degrees of freedom is 8, because I have 8 total parameters. Now, you'd be absolutely right when you said I have a total of 8 parameters, but if you look at what's happening here, well, the first perceptron is going to output from your vector valued input x in one dimension, is going to output a +1 or -1. Now, effectively, all the work is being done by that first stage, that first perceptron in the first layer. Now, if you take that +1, what are the others learning? Well, they're learning if this guy says a +1, I'm going to output a +1. If this one says a -1, I'm going to output a -1. They're not really learning anything. They're just effectively repeating what that first perceptron in this pipeline is outputting. And so the second, third, and fourth perceptron in this linear chain or set of layers of perceptrons aren't really adding anything. They're not learning anything. They're not changing the way you assign +1 and -1. They're just basically identity function. If I see a +1, I'm just going to output that. If I see a -1, I'm just going to output that. So while we have 8 parameters for this model, the effective number of parameters, meaning that you turn these knobs and something different happens, it's only 2, right? And so when we talk about VC dimension, what we're talking about is the effective number of parameters, not the raw count of parameters. Does that make sense? Okay, that's really, really important because it's very easy when you talk about VC dimension, you might pick a model and say, aha, my VC dimension is 8, and you'd be wrong, and then you'd input some data and wonder why you're underfitting, right? Gosh, well, I had 8 parameters, and I can afford a data set that's much bigger. Why am I not doing well? Because the effective degrees of freedom is only 2, even though you have 8 parameters. So yes, VC dimension kind of maps to this idea of parameters, but you want to make sure when you're counting parameters as a measure of complexity of your hypothesis set that you're looking at the effective number of parameters, not the raw count of parameters, because there's a difference between the two. Okay. Any questions about this? Does that make sense? Okay. So if we take a look at, what time is it? Okay. So if we take a look at our VC bound, we have 2 different quantities that are affecting the probability associated with the right-hand side of our augmented version of Herfling's inequality, right? And so we talked about this idea of making 2 draws of data sets of size n, and we talked about the VC bound, and we had this expression, and this expression sometimes in the literature is referred to as delta, right? Now, of course, delta is a probability bound associated with the bad event where in-sample error diverges from out-of-sample error by more than some error tolerance epsilon. And now, if we look at this growth function, we talked about this growth function or the substitute for this growth function or VC bound as being polynomial in the size of the data set. Now, of course, if the dimensionality is related to this VC dimension, our polynomial is going to have a highest degree of D, right? And so if we look at characteristically the form of this VC bound, we have a decaying exponential, and the dominating parameter for that decaying exponential, yes, epsilon makes a difference, but the dominating factor is the size of the set of in-sample points n. So we have a decaying exponential governed by n, the data set size, and then we have a polynomial whose degree is d, which is dominated by essentially the VC dimension. So if we have this particular expression, how we get this right-hand side of this VC bound to be small is by balancing the interaction between the data set size here and that degree, i.e. the polynomial, which is a function of the complexity, if you will, or descriptiveness of our hypothesis set. And so in our probably approximately correct or PAC learning model, we're going to choose some percentage, our error tolerance, but the two dominating factors are the data set size and the complexity of your hypothesis set. And so if we balance these two, we can actually examine the behavior of what happens to this probability based on these two dominating factors. So in this graph, along the horizontal axis, we have a setting of the VC dimension, the complexity of the data set size. I'm sorry, for different VC dimensions or different dimensionalities rather of the data set, which is impacts the VC dimension, we draw in a different color here, right? And so we do that in increments of 5, dimensionality of 5, 10, 15, 20, 25, 30, and so forth. And along the horizontal axis, we have n, the data set size. And so what we see is this characteristic behavior in the beginning, as the data set size is small, the polynomial term is going to dominate, right? And then eventually, once we have enough in-sample points to pay for the complexity of the hypothesis set, we start to see this decay happen, right? And once that decay happens, eventually, the probability associated with the left-hand side of Herfting's inequality, or at least the VC-bound version of it, is going to be sufficiently small so that the probability of this bad thing happening, E in diverging from E out, is a very, very rare occurrence. So what you see from this graph, we start out with the dimensionality and therefore complexity of the hypothesis set of 5, then 10, 15, 20, 25, 30, and this is on a logarithmic scale. So you can see that it's not linear, the relationship between the trade-off for complexity of your hypothesis set and the number of in-sample points that you need. So, but nonetheless, you have this characteristic domination of the polynomial term, the complexity of your hypothesis set, until eventually the number of in-sample points is big enough to pay for that complexity, and that probability of the bad event gets sufficiently small that it becomes a very rare occurrence that in-sample error diverges from out-of-sample error. And so this behavior is very regular, and this is a bound and not an exact value. But what you can see that there is a direct correspondence between the number of data points you need to pay for the complexity, if you will, of your hypothesis set. So when you choose a hypothesis set, you can't just arbitrarily choose it. You choose a hypothesis set for which you have enough data points to pay for that complexity, and you can't get around that. So if you look at this literature for a lot of these so-called deep learning networks, these deep learning networks have a lot of parameters. And why do they work so well? A lot of those examples, they have an abundant amount of data. They have millions and tens and hundreds of millions of data points. Now, of course, when you think about what happens in learning, you have a lot of parameters, right? You can't get around Herfting's inequality. You can't get around the VC bound. And so, if you go off and you look at these papers in machine learning, think about the complexity of the model, and it's not selecting the model willy-nilly. It's selecting the model for which you can pay for with data resources. You need enough data to be able to run the model. And a lot of these deep learning models, don't get me wrong, they're fantastic, but they need enough data for them to work well. And a lot of these concerns and these experiments, when they're doing deep learning, they have many millions, tens of millions, and hundreds of millions of data points on which to learn, right? But as you decrease the data set size, something has to adjust. And what has to adjust is either the complexity of the hypothesis set that you use in your model, or you have to relax the epsilon, this error tolerance. You can't get around that, regardless of what type of hypothesis that you use. And a deep learning network is nothing more than a particular stylized set of hypotheses. They're weighted sums that are passed through functions that are composed with other weighted sums passed through other functions, and they have clever ways of training them, i.e. searching through the hypothesis space. But you still can't get around the VC bound. It's just an operating law, if you will, for machine learning models. And so I'll end with this. The rule of thumb, and this isn't the hard and fast um, uh, rule, but it's just something that seems to work on many cases, that the number of data points that you can typically get away with is at least 10 times the VC dimension. Now, certainly, depending on the complexity of your model, it might be more than 10 times. But rule of thumb, you can get away with about 10 times the VC dimension as the number of examples that you need to get over this hump here, where you start to get this decay, where the complexity of the data set, this polynomial term, is no longer, this decay, rather, is no longer dominated by the complexity of your data set. You start to decrease to get past this hump, if you will. Okay? All right. Any questions about this? Does that make sense? Okay, so this is all to say that we have this beautiful framework. And this is probably one of the most important results from all of machine learning is the VC bound, right? It's the governing law, like gravity, right? You can't get around gravity. If you want to go up in the air, you have to have the force to overcome gravity, or you're not going anywhere, right? If you want to get generalization performance, you have to have enough data points in sample points to pay for the complexity or else of your hypothesis set, or else you're not going to get over this hump and you're not going to generalize well. Okay? All right, any final questions? All right, so I will end there. It is now 5:47. Ooh, I'm 2 minutes over. I apologize for that. And I will see you both on Thursday.